Hello calculus students! Today we are starting our final lesson of Unit 1. Our current learning target is limits and asymptotes, and the last two lessons have been really similar and a clear connection between limits and asymptotes. This lesson is sort of a standalone lesson, still a very important idea, but it's not as related to the other topics in the learning target. But here's our very last lesson of Unit 1, which is the intermediate value theorem. We're going to start off, as we always do, with a little warm-up. So go ahead and take about 5 minutes to solve this, and then resume me when you're ready to see what this looks like. Welcome back. So we're just going to do this together. It's a pretty quick warm-up. So if I have a vertical asymptote at -2, a vertical asymptote goes up. So I know that the limit as x approaches -2 could be any of these three. It could be positive infinity, negative infinity, or you could have even chosen does not exist. If you were imagining a limit where it's positive infinity on one side and negative infinity on the other. So any of these three answers will be good there. Nice job if you chose any of those three. And then the limit as x approaches infinity, since we have an asymptote, a horizontal asymptote at y equals 5, as x goes to infinity, it's likely going to 5 there, since that's our horizontal asymptote. Okay. This is the only answer you could put for that one. Number 2. So I need to fill in this. Horizontal asymptote, if I get a value like that, I know that it is the ratio of the leading coefficients. And so my leading coefficients, my leading terms are right here. And so I know that that has to equal 3, so my A value is going to be 3. That. And then I have a vertical asymptote at x equals 6, so x equals -6, so I know that -6 is the value that will make the denominator equal to 0. So when x equals -6, that means that x plus 6 will equal 0. So I know that x plus 6 has to be in my denominator. So I have 3x plus b over x plus 6. So my A is 3, my C is 6, so 3 plus 6 is 9. Because it wanted me to find A plus C. If you can do that, you understand the last two lessons pretty well. Awesome job. Okay, so the intermediate value theorem is going to seem kind of random, but it is actually a very simple theorem once you wrap your head around it. So go ahead and say it with me, the intermediate value theorem, just so you can get used to saying it. I will call it the IVT a lot because intermediate value theorem is quite long. But conceptually, this is what it is. So in Infinity War, Teen Groot was 5 feet 9 inches tall. So here he is, Teen Groot, 5 feet 9 inches tall. And then fully grown, Groot is 12 feet and 4 inches tall. Okay, so we have two heights that Groot was. And then here's your question. Was there ever a time in his life that Groot was 10 feet tall? How do you know that? So I want you to pause the video and answer that question, yes or no. Was there ever a time in his life that Groot was 10 feet tall? How do you know? So we're back together now, and I'm guessing most of you are like, yeah, duh. There was obviously a time, I don't know, we could draw like 10 foot. Here's my, I'll make him brown at least. Oh no, they like don't have, oh, here's kind of brown. So here, I'll draw, this does not look like Groot, but I gotta squeeze him in. Here's some branches in his hair. Here's when Groot was 10 feet tall. Obviously, sometime between teen Groot and fully grown Groot, there was a time when he was 10 foot tall. But how do you know? Sometimes can be a challenge to explain something that seems so basic. Pardon me. I need a sip. Because it just seems so obvious. However, in calculus, we do have to explain stuff like this sometimes, where we can't just say, this is really obvious, he was clearly 10 foot tall, sometime in between them. And so the intermediate value theorem is how you can explain it. So here's the definition of the intermediate value theorem. If a function is continuous between a and b, then it takes on every value between f of a and f of b. Okay, you're like, that doesn't seem related to the group problem, but it actually is. So let's let a equal teen Groot and b equal adult Groot. I don't want to use adult because that seems like a. I'll just say grown Groot. Then here's his height. So he was 5 foot 9 inches, and then he was 12 feet 4 inches. Yeah. Okay. And the key here with the intermediate value theorem is this one word, continuous. Okay? So when I connect these points between A and B, I have to draw a continuous line. So I don't really know like what his height looked like. I just know it was continuous. Okay? So obviously when you grow, you don't just like jump from one foot to another. You don't just grow a foot in an instant. You grow at a continuous pace, right? You have to meet every height in between. So since it is continuous, there's some point, I don't know what it is, we'll call it K, but there's some point here where Groot was 10 feet tall. This is optional notes just because I really want to drive the idea of continuous function home. So the top graph is another example of the intermediate value theorem. So if you have 2 points connected by a continuous curve, one point below the line, the other point above the line, then there will be at least one place where the curve crosses the line. It could happen more than once. It just guarantees that there's at least one time where that happens. However, if we have 2 points on a non-continuous curve, so if a function is a not continuous function, then you can't guarantee that there will be at least one point where the curve crosses the line. So it shows how it draws K right there, and it's like, nope, the function, even though it goes from a point that's above K to a point that's below K, if it's not continuous, there's no guarantee that the function will equal K. All right, let's look at some examples. So in both of these, we are given functions. We're given a function of a table in part A and an equation in part B. And in both of these, we have to determine, can we apply the intermediate value theorem or not? So we just have to tell, does it apply? So the following table gives us function values for the continuous function g. This is the continuous function g. So it seems like it's going to apply. So it says, therefore, there exists some r in the interval between 0 and 2. So we're just looking between these values, 0 and 2, for which f of r equals 5. So I know that f of, or I don't know why they switched. This is function g. They called it g right here, and they called it g there. So this is g. So I know that g of 2, which is 3, is less than or equal to 5, which is less than or equal to g of 0. So 3 is less than or equal to 5 is less than or equal to 7. That is true. So the intermediate value theorem applies because it's a continuous function. This has to say continuous. And then, yeah, I definitely know that there's a value where g of 5, or g of r, I don't know what value of r or x. This should say x. Yikes. So there's a value of x for which g is equal to 5, because 5 is between 3 and 7. So yes, it applies. G of x is a continuous function. And g of 2 is less than or equal to 5 is less than or equal to g of 0. Since we are just looking on the interval between 0 and 2, those are the x values we're looking between. Cool. And then part B, let k be the function defined by this piecewise function. So now I've got a function. There must exist some x between 0 and 2 for which k equals 4. We've got to check if this is a continuous function. It's important that this function is continuous. So in order to check continuity, let's check to see does the limit as x approaches 1, since that's my transition point from the left of k of x, does it equal the limit as x approaches 1 from the right of k of x? So the limit as x approaches 1 from the left will be 1 plus 2. The limit as x approaches 1 from the right will be 1 plus 4. So we were checking this. This was always a question mark, and we see it does not. So this is not continuous. The IVT does not apply because k of x is not continuous. Okay, we always have to check if it's a continuous function. If it's not, IVT does not apply. And that's directly because of this reason. We can't make the assumption because, if it's not continuous, there's places where it doesn't have to equal any value between f of a and f of b. Okay. Example 2. Selected values of a continuous function f are given in the table above. What is the fewest possible number of zeros of f in the interval between -1 and 2? So here's just a little vocabulary review. Zeros is a synonym for like x-intercept, and that happens when f of x equals 0. So we're looking to see how many times, what is the fewest possible number of zeros or times that f of x equals 0. And we're looking specifically in this interval between -1 and 2. It's a continuous function, so I know that IVT applies. So I'm just going to write that down. So if the function goes from 5 to 2, in a table, I don't really know what's happening. I know that it could have gone down to 0. Like it could, between 5 and 2, it could go down to like -3 and then go back up to 2, but I can't guarantee it. So I can only count the ones that I know definitely happened. Between 2 and -4, in order to go from 2 to -4, I know that the function had to go through 0. So this is one time for sure. And then from -4 to -1, it could have gone through 0, but I don't know. So I can't count that. So I can say that there is at least, there is at least 1 0 of f on 0 to 2 because f of 0 is less than, is greater than or equal to 0, which is greater than or equal to f of 1. So I know that 0 occurs between 0 and 1, which is on this interval. Okay. This is a very similar problem, another graph, or another table. The function is continuous on the closed interval 0 to 2, so I know that the IVT applies. And has values that are given in the table above. The equation f of x equals 7 must have at least 2 solutions in the interval between 1, this should say between 0 and 2. If k equals what? So we're looking between 0 and 2, and we want this equation f of x equals 7 to have 2 solutions. So I think I'm gonna kind of do a rough graph of this for you to be able to visualize. So between at 0 we're at 6, at 1 we don't know where we're at k, and then at 2 the function is down here at 5. Okay, so I know that at 0 the function is equal to 6, I'll use black, 6. And then at 2, the function is 5. Okay. But I want f of x to equal to 7 at 2 points. So here is f of x equals 7. I'll draw it in red. There's the solution. F of x equals 7. And I want that to have 2 solutions. So I want my curve that connects these 2 black points to pass through that red line twice. So I know that it has to go up and over and then down back through it, so that there's 2 solutions right there. Okay. And now I need to estimate what is my value of k. So k is the y value at 1. So my only option here is 8. It's the only one that works. 7, choosing the answer 7 might be tempting to some people, but if you look at it, if it only touches the curve at 7, that only guarantees 1 solution. And we wanted to have at least 2 solutions, so I know it has to go through. So 1 has to be above to guarantee at least 2 solutions. Alright, so that is the intermediate value theorem. I know that these examples can seem a little bit confusing, but I really want you to consider that this example with GROOT is really all that the intermediate value theorem is. If you have 2 points and there's a continuous function between the points, the y values, all the y values in between f of a and f of b are going to be solutions in the equation. So if you're having a hard time wrapping your head around it, please just remember it is as simple as this GROOT example here.